Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is evaluate division. So let's go to LeetCode. Alright, there we go. You are given an array of variable pairs called equations and an array of real numbers called values, where equations at ith position represents a pair A and B, and values ith represent the equation A divided by B. So A division by B, and that value is present at the values ith position. Each A or B is a string that represents a single variable, by the way. So you are also given some queries where queries at jth position basically has two variables C and D represents this query. Basically the answer would be C divided by D. Now we need to return the answers to all these queries. If a single answer cannot be determined, if you are calculating that query and there is no basically through all the equations given right here, you cannot make a pair A divided by B or C divided by D, then you are going to have -1 there. The input is always valid. You may assume that evaluating the queries will not result in division by 0, and there is no contradiction. All right, so the variables that do not occur in the list of equations are undefined, so the answer cannot be determined for them. Basically the answer would be -1 over there. All right, so let's go over it. This is by far one of the easiest problem on a graph. Honestly, I'm not even kidding. I sat down and I solved this problem within like 5 to 10 minutes, along with the solution I'm talking about. So let's go over it. We're taking the first example. Let's understand what the problem has given us in the input. So we are given equations, values, and queries. These two right here are very well connected. Here equations represents value A and B as pair. These are string values, by the way, and the values is corresponding to these equations represents the calculation. So A, B here, this values represents A divided by B. This is the value right here, and B divided by C is the value right here. And then we are given these queries. We have to find answers to these queries. So basically this will be the answer right here, this will be the answer right here, and this will be the answer right here, and so on. All right, that's what we need to do. So here A and C is directly not given in the equations to us. We have to find it. We have to find a path from A to C. Sorry, I said path, but you guys be like, what are you talking about? What do you mean path? Well, let me tell you, this equations right here, we could represent these values, these pairs, as nodes in our graph that we are going to create. So we are going to create a graph. So let's say I create a graph with node A, and then I will have an edge going to B, and there will be a weight associated with this. So from A to B, the weight would be 2. I'm going to say 2. Why? Well, it's given to us in the values. So this is the weight from going from A to B. But how about B to A? So if you know mathematics, so A divided by B is 2, then B divided by A is 1/2, right? So the weight, and at this point I'm just gonna basically I want to create our graph really nice here. So I'll just redraw this edge. So here from B to A, the weight of this edge would be 1/2. How about the second equation, B to C? There is a path from B to C. So from B to C there is an edge. So C is going to be a different node. B already we have created as part of the first equation. So the weight here is 3, and the weight from C to B, just like we calculated for this one, we're going to do the same thing. So if B by C is 3, then C by B is going to be 1 by 3. All right, so now we understand that very well. So I'm going to get rid of this so that we have really nice looking graph right here. So this will be 1 by 3. All right, and I'm going to just, like, for simplicity, I'm going to get rid of these zeros. All right, now we have this graph created with us. Then we have all these queries, and we are going to solve these queries by basically solving a problem in graph. Like, if you're given two source and destination nodes, find the cost of going from source to the destination node. That's exactly what we are doing. If you do not have those nodes present in your graph, then you're going to return -1. So we are going to calculate answers for this. Let's say we're calculating answers for this. I'll move this right here, and I might even make it a little smaller. All right, make it a little smaller. So A to C, is A present in my graph? Yes, it is. Is C present in my graph? Yes, it is. Are they connected? Well, not directly, but indirectly, yes. So what we are going to do is we're going to run DFS on it. We'll be running DFS on it, and I think let's put it right here, and then I'm going to write the DFS code right here. So DFS. So DFS would be from U, the source node, to V, and then we'll also have a visited set. This time this visited set will be unique to each query, because you cannot have a common visited set. We'll have to reset every time you run, it's an individual query from source to destination that we are finding the path. So we'll put in A and C inside this. So first will be, by the way, I will actually, before I start running these queries, I will create the graph adjacency list, which will have basically this entire thing that we have just created, but in a different format. What would be that format? Well, let me just show you right here. So in my graph, I'm not going to write the entire thing, but just a little bit. So in my graph, the adjacency list, what I'll be having is, because I could see that A and B are connected together, and I have basically connected them, and it has two paths, basically from A to B and B to A. In other words, you can say it's an undirected graph as well, but the weight here is going to be flipped. Basically, it will be reciprocal of the weight from A to B. So B to A will be reciprocal of the weight of A to B. So now here, what I'll do is I'll have all these nodes. So A, B, and C, and all these nodes are going to have the neighbors that they have. All right, the neighbors that they have. All right, so what are neighbors of A? Well, A's neighbor is B. A's neighbor is B, but at the same time, what I'm going to store is the weight associated with that. Then there is basically a path from B to A as well. So here as well, I will store A, but at the same time, I will store 1 by 2 as weight. Then there is a path from C to B to C, So I'll write that C, and then, my bad. From in this B, there is a path to C, and the weight is 3. And the reciprocal of this would be, there is a path from C to B, and the weight is 1 by 3. So that is all. That will be all. That is the entire graph, and I have written all of it. All right, I have written all of it. So I am going to actually just minimize it a little so that you can look at it nicely. All right, so this is the entire graph that we have. Now we'll be running to find the answers. We'll be running the queries. Okay, so this answers. So what I'll be doing here is, for each query, I can call it U and V. u and v, and then I'll have my answers array that will store all the answers. So for u and v, so source and destination in queries. So and then I will basically answers dot append, and then I will send in u and v and a visited set, but I'll just call it an empty set, just an empty set that I'm sending. And in the end we can just return our answer, return answers. All right, let's go into DFS. That is the core of our solution. So here we have our source destination, which is u, and the destination node, which is v. So if neither of them exist in my graph, then I will be returning -1. That was asked in the problem. So if u not in graph or v, I think a better way would be just writing u or v, not in graph, then return -1. Well, if u becomes equals to v, then you return 1, because what is the cost of going from A to A? A is connected to itself, so it's going to be just 1, so return 1. But then we are going to add, so visited dot add this u, and then we're going to visit all the neighbors of u. So I'm just gonna squeeze this code here a little bit, and then for let's say, so if you remember here, we stored these values right here, we stored them like as pair. So here we'll have to be a little careful how we are visiting. So I'll just say node, for node in graph of u. So this will give me two values. First will be the neighbor, I'm gonna call it neighbor, and then weight, that I will unwrap those values from my node, right? We stored them right here as the node, the neighbor, and the weight. Finally, what we'll be doing, if this neighbor is already visited, so in visited, then what are we gonna do? We just continue. So we'll continue. All right, we'll continue. But if it is not, then what I'll be doing is I'll be calling it, basically I just need to get to the destination from this neighbor, and it will be bringing me some value, either 1, -1, or some calculated other value, which we are going to just do it here. So I'll call it sub, like it's a sub problem, so I'll call it sub, and I will call DFS on this, which is the neighbor, and this neighbor will take v as well, which is the destination node. And then for the visited set, because it's part of one query, then I'm gonna send the visited set itself. If this sub is not equals to -1, that means it brought me some value, and we have already found basically our answer. So -1 means we have not found any of these nodes. That's when you receive -1. If it basically returns 1, that means you have found your answer. But if it might return some other value as well, which will be we will be returning right here. So we will return what? W, which is right here, weight into basically sub. So sub. So this weight right here, because you took this node's help to get to the destination, which is v, and this sub is basically the cost of getting to that node from this v or neighbor. So this is what we return right here. Okay, you couldn't see this part, so I'm just gonna even squeeze it a little more. All right, so now you can see, and this is exactly this is exactly what we will be writing in our answer, and you'll see how easy it gets for us to just translate this pseudocode into our answers. So let's implement our solution. By the way, the time complexity is going to be, well, this DFS takes the time complexity of this particular DFS is big of v plus e, the time complexity, and maybe I should write it a little nicely. So the time complexity is going to be big of v plus e, and then space complexity is also going to be v plus e. But remember, for this is, I'm talking only about this DFS, but here let's say the number of queries is k, so it's k into, so time complexity would be k into big of v plus e, vertex plus edges, and space is also, well, it's for space we are actually we are resetting this visited set, and that's the only space that we are using, so it's only going to be v plus e. So that is it. Let's implement our solution now. Okay, there you go. Let me just arrange it a little nicely. Okay, so first thing first, let's create our graph, which is going to be a dictionary. So let's call it default dict of type list. Then let's go over for we can say for I and this a comma b enumerate. What are we enumerating? We are enumerating equations, and the reason that I have taken this I here is so that I can get the cost from the values, all right, to associate it with this path from A to B and B to A. So here I'll say this graph has a path, so I'll append to A's neighbors B, but at the same time, this time I'm not just appending B, I'm appending B and the cost. So the cost would be from the values. We can just copy values and get the value at the ith position, and then we can do vice versa, because if A is connected to B, B is connected to A, but the cost is reversed because it will be reciprocal of what the cost was from A to B. Alright, so I'll just basically have this value divided by 1 divided by values. Alright, so our graph is ready now. Graph is ready. Here we will be implementing the function DFS, but before we do that, let's write down the code. We'll come back to it later. Let's write down the code for our answers. Answers would be an array, and for equations, this query will be giving me source and destination. So this in queries. So here I will just say answers.append DFS, and this DFS will be taking in these values. And remember, we are going to send a visited set, so I'll just send in like empty set right here. And then finally we can just return our answer. Alright, so that is it. Make it look a little nicer. Okay. Alright, so let's implement our DFS. We'll have source, which is U, then destination, which is V, and then visited set. Base case would be if this U not in graph or V not in graph return -1. If they become equal, U is equals to V, then you return 1, because cost of going to itself, like cost of a node going to itself, is 1. Well, it's not 1, it's 0, but we are going to return 1 because we'll be multiplying it with the other cost that we have, you know, accumulated to get to basically that node. Here we'll mark this U visited. We'll mark this U, this visited U visited, and then we are going to explore all the neighbors of U. So for node in graph U, so this will be giving me the list of neighbors, but at the same time it's also giving me the list of values as pairs. So neighbor and cost, so I'll call it W, so weight, so I'll just call it weight itself. So neighbor and weight is basically, I'll unwrap these values from node, and if I have already visited this neighbor, so this neighbor in visited, then I can continue. So continue. Otherwise I will take this neighbors, you know, path, so I'll visit neighbor, but from there I'll call DFS to get to our destination node. So here I'll just call it like sub problem, and then it's taking DFS neighbor node, then it's going to take basically the source, which is V itself. We are not changing, sorry, this destination, V is the destination, we don't change that, and the same visited set. And if it doesn't return -1, so if this sub is not equals to -1, then I will return, because I am now, if it returns something, that means it didn't return -1 from here, or maybe in the end, you know, like from here, -1. If it returns some value, that means we have found this right here. It either returned 1 or returned itself, like this function itself, but like maybe coming from the neighbor node of this neighbor. Okay, so here I'll just return sub into the weight that we just received from the node to get to that node. All right, so that will be all the code for DFS, all the code for the DFS. And let me zoom out so you can see the entire code. All right, there we go. Okay, let's run and test it on our examples. I hope there is no typo. Yes, there is not, so let's submit it. Awesome, 100%. So we talked about the time complexity and space complexity. Let's write it down. So time complexity, as I said, if k is the number of queries, so it's going to be big of k into v plus e, because for all the queries we are calling DFS. DFS time complexity is v plus e. So where k is number, so I'll just call it number of queries. All right, so and then for space complexity, is going to be big of v plus e. So you can talk about it like either from yeah, like from this graph, because we are storing, like, you know, so it might be like 2 into not even 2 actually, it's just v plus e. All right, so we're done. Let's go to AlgoYogi, mark this problem solved, and see you guys later in the next problem. Until then, bye bye.